Hi, my name is Karina Slater, and I'll be talking about Lab 7 today. The objective of this lab was to find a mass of a black hole located at a given position by examining the motion of a star from given position points that is being acted on only by the gravitational force of the black hole. And my result was that the mass was 2.17 times 10 to the 31st kilograms, which was confirmed to be an accurate mass by WebAssign. Now I'll explain the process by which I found the mass of the black hole. I was given some initial conditions, and here they are. You can see them in the box in the right-hand corner. They include the mass of the star, the time step to be taken, which is 1 day in seconds, and the file that contains the position data for the star. I started by finding x and y velocities for each position in the position data given, and I did this for each set of 2 points. I took the second point minus the first and divided by the time step. And I did this because the velocity is equal to the change in distance over the change in time, and so I could find the velocity for x and the velocity for y for each position. So from there, I started calculating the net force, the parallel net force, and the perpendicular net force. I did this by using the velocities that I had just gotten to find an initial velocity and a final velocity vector. And I just used that the momentum equals the mass times the velocity when the velocity is small compared to the speed of light, which it is in this case. And that's how I found the initial and final momentums, which you can see in the first red box. Then I found the change in momentum just by doing p final minus p initial. F net equals the change in p over the change in t, so delta p over delta t. Then to find the parallel and perpendicular components of the force, I first started with the formula for the parallel component, which you can see on the screen in the second red box under the heading parallel and perpendicular components. I found the change in magnitude of p by just taking the magnitude of p initial and the magnitude of p final and doing p final minus p initial, dividing by the time step, and then multiplying by p hat. And p hat is a unit vector, which I made to be p initial divided by the magnitude of p initial. And from here I got a vector that showed the parallel force component. Then I just used the fact that F net equals the sum of the parallel and the perpendicular component to find the perpendicular component, because I know F net and I know the parallel component, so I just did F net minus the parallel component to find the perpendicular component. So now I had all the information I needed to find the mass of a black hole, and I did this by recognizing that the net force exerted on the star that's causing its motion is the gravitational force of the black hole. So I just made the magnitude of F net equal to the formula for the gravitational force, and I said the magnitude of F net because I wanted the mass of the black hole to be a scalar because the vector would not make sense. So I just solved for the mass of the black hole, which I'm calling M2 as you can see on the screen. And I used the position of the black hole given to me in the problem and the final position of the star for R. And I ended up getting 2.18 times 10 to the 31st, which was confirmed kilograms, which was confirmed to be an accurate mass by WebAssign. So what does this mean? On the screen you can see arrows representing the net force, the parallel force, and the perpendicular force. And we know from the momentum principle that dp dt equals F net, and so it follows that dp dt parallel equals F net parallel and dp dt perp equals F net perp. So mathematically these things are equivalent, the F nets and the dp dt's. However, they are different in a sense. Force causes the change in momentum. So without the force, we wouldn't have the dp dt. And when we look at the dp dt to calculate the force, we aren't saying that the momentum causes the force to be this. We're saying that because we don't know the force, we look at the momentum, and from there we can infer what the force is because the force causes the change in momentum. So what if a different black hole were placed at the same location as the original black hole, and the motion of the star remained unchanged? Could you find a different mass than the one you found for the original black hole? And the answer is no. Just as explained in the previous slide, we base our prediction of the mass of a black hole on the force it exerts on the star, and we predict this force by looking at the motion of the object. So if the motion of the object remains unchanged, the calculated force will remain unchanged, and so the predicted mass will remain unchanged.